So when we go to convert these to z-scores, the mu and the sigma are going to stay the same. So this is going to be 25 for both, and this is going to be 0.21213 for both. The only thing that's going to change is that front number. So let's start with the 24.7 minus the 25 average over 0.21213. And then the other one will be the 25.5 minus the 25 average over 0.21213. All right. So remember, z-scores are rounded to 2 decimal places. So when you guys do that first one, when you convert 24.7 to a z-score, what do you get for a z-score? Negative something. Oh, make sure you do the subtraction first and then divide by it. Does that make sense? Or put parentheses around it. Because your z-score shouldn't range much outside of -3 or +3, okay? So if you get like a 90 or 12 or something, you're usually off. What do you guys get? Does that look okay? -1.41. And then what do you get for your z-score when you convert 25.5? 2.36, perfect. Which this kind of, I know you guys don't think this way, but I get my mind blown a lot. 24.7 compared to 28.5 minutes, that's like how many seconds difference, you know what I mean? And this is only 30 seconds difference. And look how far out we are. We're a standard deviation and a half, and we're more than 2 standard deviations away. So we're shading a good chunk of our graph, okay? So zero's in the middle, we're at -1.41 here, and then 2.36, guys, is pretty far out there. Sorry my picture's so ugly, but okay. So 0 is always in the middle of the standard normal curve, and then our value of 24.7 got changed to a z-score of -1.41, so almost a standard deviation and a half lower. And our value of 25.5 is way over here at 2.36. So we're shading a good chunk of our graph. So when we go to look up the answer, the areas that go with it, it should be a pretty high answer, okay? Because we're pretty far out there. We're shading a lot. So do you guys remember what you had to do when you had 2 z-scores, how you find the area in between? Subtract the 2, yep. So we're going to look up 2.36 first. So z equals 2.36, and we'll come up with his value, and then z equals -1.41. So 2.36, I got 9909. Does that look right? 2.3, there it is, 6. And then -1.41, I got 0.0793. Okay, so I got a difference of 9116. Again, that would be, yes?
I think it's 9906.
Is it 9906?
Yeah.
Let's see, 2.3 and then 6. But be careful because that first column's 0. So you count 7 over. So 1, 2, 3, 4, 5, 6, 7. Right? Do you see that?
Oh, okay.
Because that 0 column, you don't think about it. So we're going over to the 6th column. So 9909 minus a 0.0793, this would be enough to just type into my math lab or circle it for my test or whatever it means. But in a nutshell, what did we do? We said, okay, the probability that the average commute time was between 24.7 and 25.5 minutes. We said, well, shoot, we don't have a chart that tells us average commute times. So what we did was we changed our x bar to a z. So we really want to know the probability that z was between -1.41 and what was it, 2.36? And that was the 9116. Which, guys, that's pretty impressive. So we didn't even have a span of like a minute, right? We didn't even have a span of a minute straddling our mean, and over 91% of the population is in that range, all right? And again, if we took 1,000 samples of size 50, how many of them would have a commute time between these two ranges? 912, okay? So 1,000 samples of size n equals 50 would have 912 with a commute time between 24.7, and 25.5. So that 912, again, is coming from multiplying your percent, your probability, your proportion, by whatever your sample size was.